To begin our study of Kepler's laws of planetary motion, we'll start with, who were these people who came up with the laws, and what are they, and then we'll get into the proof of the first law. Johannes Kepler was a German astronomer, lived in the 1571 to 1630, and he had actually worked under another astronomer, Tycho Brahe, who was a Danish astronomer, a nobleman who actually owned an island and created a research institute. And what Tycho did is he had, in his research institute, he actually did very, very minute calculations of observations, I should say, of positions of the stars and the planets. Very, very detailed. I mean, incredibly detailed, and the precision was phenomenal. And so, as an assistant to Tycho, Kepler had access to this information, and later went and looked at, the locations of where the planets were, and came up with some observations which, again, you think about, boy, no computers, no calculators. To notice some of the things that he noticed are incredible. So let me show you what he came up with for these laws. Okay, the first law of planetary motion is known as the law of orbits. And what he noticed is that all the planets moved in elliptical orbits around the sun, and the sun was at a focus. And so we're saying mathematically precise ellipse, and the sun is at that mathematical point, we call a focus. So having studied ellipses before, we're going to be able to use that information to make some connections. Let me illustrate what that law kind of looks like. So we have, this orbit of a planet along this ellipse. Sun is indicating at a focus here. And just to remind you some things about ellipses, then, we have something called eccentricity or eccentricity, depending how you want to pronounce it, this E thing. And that sort of describes the stretchiness of the ellipse from a circle. So a circle has eccentricity of 0, and then as eccentricity approaches a value of 1, the ellipse stretches further and further out. Now, this particular drawing here is quite exaggerated because most planets, although they, aren't elliptical shapes, they're actually pretty close to looking like circles for the most part, okay? Pluto, whether you want to call it a planet or not, it also follows, the orbital mechanics here. That's the most stretched out one. Mercury's a little bit stretched out. But this also applies for comets, which definitely have very high eccentricities, okay? Let's show you a little example here. So here we can, we've got our sun, you can read this information up here. So we're going to put a planet on here and give it some initial velocity and send it on its way. And we can watch sort of the orbit that's created from this. And this one, has a little bit of a eccentricity, a little bit off from being a circle, because the sun is not at the center, which it would be in a perfect circle, right? We can play around with this. I'll make sure to include this link on the website also. Well, let's see. Let's shoot it off that way, see what happens. Okay, that's going to have a much wider orbit. Let's probably go off a little bit off the screen. But it should come back eventually. Do we wait for it? What? Why not? Here it comes. But it should connect back up again. So we're always going to have these orbits connecting back up. Whoa, it missed. I guess this one's not going to quite stay in orbit. That's kind of interesting. You can also do some other things like try to send it off the other direction and watch the gravitational force pull it in. Oh, crash! I'll make sure to link it. I know you'll want to crash some planets. So that's the first law.